Hello, everyone. My name is Peter Pavelski. I'm an electrical engineering senior student graduating this semester from UMass Amherst. I'm here to present my honors research about numerical simulations of thermal transport of 2D materials. It was guided research associated with the Nanoenergy and Thermophysics lab here at UMass under my primary chair, Professor Examia, with assistance from my secondary chair, Professor Anderson. Before we begin, here's an overview of what to expect from this presentation. First, I'll be providing a taste of the main ideas related to my research. Next will be an introduction to topics related to my code to help the audience understand what is happening better. After this will be explanations about the methods and the code I used in my research to develop my results. This will then transition into seeing some of these results alongside some interpretations. Lastly, I will finish off with some key takeaways and mention possible next steps for this project. All right, let's start. What I hope to do with my research is create a tool for simulating thermal transport of 2D materials. This brings up the idea of why we should care about thermal transport, especially for 2D materials. First, as shown on the figure, the number of transistors per chip is rising every year. This plot, demonstrating Moore's law, depicts the most common worry many energy engineers are aware of. Focusing on the red triangle points, we see that the typical power is leveling out. This is related to poor heat management on these chips, causing the performance of essential components to worsen. With this supports a high demand for options to help with this heat problem. Regarding 2D materials, they have become a promising solution to heat problems as they help with scaling devices down and have shown great potential in becoming fundamental building blocks for the next generation of electronics. Moving forward from this, my research involves using MATLAB code that simulates heat movement by solving the Boltzmann transport equation with the Monte Carlo method. The results from my code have shown to be promising and has the potential of becoming a powerful tool for guiding future studies of high conductive 2D materials. Transitioning into the intro, let us begin with the definition of temperature. Seems trivial to ask, but it is an important starting point. The general definition is the average energy of a system of particles in equilibrium. This definition holds true, but only in larger systems. Since we're looking more in the nanoscale world, temperature is described as the distribution and density of phonons. Now, when the movement of these phonons is interrupted, this introduces another topic of phonon scattering processes. Now we have two ideas to think about, phonons and scattering. Think of phonons as the particles of heat as photons are the particle of light. There are multiple ways these phonons can scatter, but my research focuses on the three phonon scattering type. If you look at figure 2, you can see events that can occur when three phonons are involved. As a side note, the dashed lines are different energy levels, and crossing into the region on the right represents entering a higher energy level, while entering to the left is a lower energy level. These scattering mechanisms can be grouped into two main groups, normal and umklapp. Normal or end-scattering occurs when the process produces a small wave vector that falls outside the first Brillouin zone, or FPZ, as shown in figure 3a. This zone is just a fancy word for momentum space. This zone is important because the behavior of this single cell can completely characterize all other cells in the structure. Regarding umklapp or U-scattering, this occurs when a process produces a large wave vector that falls outside of the FPZ. Since we only want to focus on the inside of the FPZ, this vector pointing outside of the region can be represented as a point inside, as seen in figure 3b. Due to the process of changing the vector direction, this destroys momentum. End scattering does not do this with the wave vector, therefore momentum is conserved. These U-scattering processes are important to study as they directly relate to thermal transport resistance. The goal for many researchers is to have end scattering be the dominant scattering mechanism inside of a material as it causes the least thermal resistance. This, however, is difficult to achieve as end scattering is relatively weak compared to U scattering. End scattering and U scattering influence thermal transport in different ways, relating to three regimes of transport: ballistic, diffusive, and hydrodynamic. For this research, we focus on the diffusive and hydrodynamic regimes. Figure A depicts the diffusive regime, and what we see is the density of phonons decreasing as you move farther from the heat source. Phonons are slowly diffusing or moving away from the heat source and each other, causing the heat to slowly flow. This happens when U scattering is the dominant scattering mechanism. Regarding the hydrodynamic transport regime, this is a special way phonons can move, but it happens under very specific conditions. What figure B shows is the phonons moving in a wave formation. From this, heat moves fluid-like, allowing for extremely high thermal conductivity. This is when normal scattering is the dominant scattering mechanism. Lastly, in our introduction, we asked the question, what are the Boltzmann transfer equation and Monte Carlo method? The BT is an equation that describes statistical behavior of thermodynamic systems. Looking at the equation to the bottom right, important terms in it are to notice are F, where it is the distribution function of phonons, and phi, which is the scattering rate from state K prime to K. With these complexities, solutions to the BT are difficult in deterministic means. Now regarding what the Monte Carlo method is, it is a broad class of computational algorithms that uses randomness to solve problems that might be deterministic in principle. This segues into the next section of how these two are used together. Let's start off and mention why the BT is chosen for this research. The BT approach is the most desirable for us because it provides simulations of individual phonons in more realistic sizes and geometries. We are able to look at the individual phonons, allowing for a more in-depth insight of interaction that is unable to be seen in most other methods or even physical experiments. Looking at the flowchart on the right, we see a general guide on how my code treats the BTE. The maroon boxes now on the flowchart are the places where the Monte Carlo method comes into play. A lot of randomness is used in the code, but the best example would be the maroon box at the bottom, where random phonons are generated until they are suitable to represent the final state of phonons after its scattering event. The final product of this code is the thermal conductivity of the materials. Provided here is the equation used to calculate it. All values except kT are constants. KT is an important value as it tracks and compares each phonon's velocity to their initial velocity in the beginning. What we're essentially doing is tracking how fast these phonons move into a steady state. Next, here's a quick slide to emphasize what I did in this research experience. The MATLAB code has a main file that calls these 11 subfunctions. This code started off as a 3D version made by my primary chair. I was to make this code into a 2D version specifically for graphene. It sounds like it should be easier, but it is not, as the physics of the phonons changes a lot in 2D space compared to 3D. This required me to understand the physics going on and as well understand the techniques done in the code. We also see in the figures where these subfunction MATLAB files are mainly used to solve the BT with the Monte Carlo method, as aforementioned in my previous flowchart. Here is an illustration of what one of my subfunctions does for the overall code. This subfunction loads in phonon dispersion data that was generated using a first principles calculations modeler, Quantum Espresso, made by another member in the lab. What these plots show us is the relationship between omega and its momentum point. This omega value can be converted to energy and velocity, thus allowing us to make a table of values when a phonon lands on a specific momentum space. Moving on to my results, here are some plots visualizing random phonons I generated in my simulations. Looking at the figure on the left, we see a less active phonon where it scatters twice and goes in a single direction without interruption afterwards. The figure on the right shows a different story where we have a phonon scattering and changing directions many times. This behavior of changing directions is not desirable as it relates to the resistance in our flow of heat. The next couple of slides are used to show support for the functionality of my code. Looking at figure A, we want the overall energy to stay constant. We see it rising, but looking at the scale, it tells us this change is negligible. In the next figure, figure B, we want to see the energy of each branch stabilizing over time, as this tells us the phonons are reaching a steady state of a constant heat flow. While lastly, figure C tells us the number of phonons deviating or acting out of place or acting out of character over time. Compared to our total of 10,000 phonons in the simulation, these numbers are small, which shows good signs for us. Here we see a plot of our phonon velocity autocorrelation data as mentioned in the previous section. The behavior we're looking for is the autocorrelation to decay to zero. This tells us that the phonons have a weak relation to when they have started and have reached a steady state. Next, I ran the code to only contain umklapp scattering. I do this to further check the functionality of the code, but also because I want to highlight the significance of umklapp scattering to the thermal conductance of a material. This will simulate the diffuses regime of phonon transport. We see the same expected behavior as mentioned before, so these are further good signs. Here we see the main product for both simulations of my code. I calculate the thermal conductance of graphene over a range of temperatures. First, we compare this compare this plot to data found in a paper by Y. Guo and his associates. We see a similar shape and decaying nature. This decaying shape makes sense as higher temperatures mean more photon scattering. However, there is one main problem with the magnitude of my data. Overall, similar behavior occurs, but there is still debugging needed to be done in my code for more accurate results. Still with this, we do see that the umklapp scattering indeed shows hindrance to the thermal conductivity of a material over most temperatures. This supports the notion of how normal scattering raises the material's thermal conductance. Now we reach the final section of the presentation. To start off my key takeaways, I have developed stronger software development skills that allowed me to create code that solves the Boltzmann transport equation. We saw how umklapp negatively impacts the material's thermal conductance, supporting how we instead want more normal scattering for higher thermal conductivity. This is what happens in the hydrodynamic transport regime, so it is logical for us to look more into its conditions for future simulations. It would also be beneficial to incorporate boundary conditions so we can simulate below 100 Kelvin and also use other 2D materials similar to graphene to further our scope of knowledge. I thank you all for listening to my presentation. I hope you all have a nice day.